All right. So let me put up the whiteboard. So before I get started on anything from Module 8, were there any questions over what was covered last time you guys met? Module 9? I don't think Module 9 is too bad. Just a bunch of like rules, I think, is the main part. Rules you have to remember. But yeah, if there are no questions, then we go and jump into Module 8. So Module 8 is the introduction of equilibrium, which I'm sure you guys are all familiar with. Module 9 delves deeper into equilibrium. I'm sure you guys have covered it in lecture. So we're starting on page 209. I'm kind of going to read through Module 8. Maybe not word for word, maybe just summarize things mostly. But yeah. So page 209, at the top of the page, it gives us some formulas that we need to know. And these are super generic. So we have Kc, we have Kp, and then we have another way to relate Kp and Kc. Kc, C is for concentration, P is for pressure. So you can see that Kc is equal to concentration of products over reactants. And all these are raised to their stoichiometric coefficients. So big C to little c, big D to little d, big A to little a, and big B to little b. And the same for pressure. So we see the pressure of C raised to the value of little c, pressure of D raised to the value of lowercase d, and then PA to the power little a, PB to the power little b. And and one more thing to note with all these formulas, where's my pen? We see that Kp equals KRT delta N. So can someone tell me what is delta N? So we have, let me see, Kp is equal to KRT delta N. Can someone tell me what is delta N? Do you guys know? No? Change in moles. So let's look at that top of the generic formula that's given to us. So we have A plus B yields C plus D. So delta N would be the change in moles. So it'd be all the moles from the final, or the product side, minus the initial. So it'd be like D plus C minus A plus B. Gives us our change in moles. So that's our delta N. The beginning of the module kind of goes into what is equilibrium. So it's when a reaction has the same rate going in the forward direction as well as the backward direction. So it's kind of an equal push and pull between both sides of the reaction. That's why we use the double-sided arrow as opposed to a one-sided arrow. So yeah. It goes on to say equilibrium can be approached no matter what the starting position is. And what that really means basically is, let's say we have calcium hydroxide, it's supposed to be parentheses, dropped into some water. And we know that this is a weak base, so we know it's not going to dissociate completely. So we know there's going to be at one point an equilibrium where equilibrium is reached, where there's a certain amount of calcium hydroxide molecules and its substituents, calcium ions and the hydroxide ions. But let's say we also have a scenario where we have a same amount of volume and everything, same jar, but instead we drop in calcium ions as well as a bunch of hydroxide ions. And let's say we drop in no calcium hydroxide. Because equilibrium can be reached no matter what the starting position is, what's going to happen is it will start to go in the reverse direction. So out of here, we'll get the production of calcium hydroxide. This is just an example, but I hope that makes sense to everybody. Whether you're starting with all of your reactants, which is how we kind of like to think about things. We start off only with reactants. This is module 8. I was told you guys went over module 9 last week. So yeah, let's say we start off with mostly products. Those products will kind of act as reactants in the reverse reaction. So it's kind of a, well, yeah, you reach equilibrium. So that's basically that. We have it goes on for some practice exercises. So we can go through those. So the first one reads on 210, if a reaction has reached equilibrium and the rate of the forward direction at equilibrium is found to be 2.5 10 to the negative 4 molar per second, what can you predict about the rate of the reverse direction? So what do you guys think? Any guesses as to what's going to be the rate going backwards if we're at equilibrium?
It's the same?
Yeah, so it would be the same in the opposite direction. So we could say that the rates of the reverse direction would be like 2.5 times 10 to the negative 4. And we could say it's a negative. Since it's moving opposite the forward direction, we will, it'll have the same rates, but kind of opposite. So once they're at equilibrium, they just cancel each other out. So yeah, let's look at that next one. So the reaction A goes to B is begun such that the forward rate is 6.2 times 10 to the 9, and the reverse is 2.8 times 10 to the 6 under the initial condition. What, if anything, can be predicted about the rate of the forward direction when the reaction reaches equilibrium? So, what do you guys think?
The forward, I think it's a decrease.
And what about the reverse?
Increase.
Yeah. So you kind of think of it like we have this forward direction, the rate of the forward direction. So K forward, and right here we have K in the opposite direction. And eventually, once they reach equilibrium, they're going to meet somewhere in the middle. They hit that sweet spot, and that'll be our equilibrium. So in the reverse will kind of go up, and in the forward, it'll kind of come down a little bit until they reach equilibrium. So yeah, are there any questions on equilibrium as a concept? No. And then just to clarify, um, going back to that kind of example I had said earlier, where we start off with mostly products, it could also be described using like this little diagram that I had drawn. So K in the reverse and K in the forward direction. This would be what would happen if we had mostly products. So it's going to go backwards more than it is going to go forward. So we'll have the production of reactants until they reach equilibrium. And yeah. So moving on, we have on 211, it goes into K at equilibrium and tells us a little bit about our Kc expression. If I'm going kind of fast, just let me know. I know you guys kind of already went through this in lecture maybe a little bit ago. So I'm sure you guys are all pros at this. But yeah, so K equilibrium is basically products over reactants. And it goes on to tell us that we could be more specific about what type of K we're using. So we can use concentration, and that's our Kc. Kc is a unitless quantity. And this is going to be at equilibrium. I know you guys went over module 9, so where you were introduced to Q, and that's basically the same equation, but at any point besides equilibrium. But K specifically equilibrium. And we could see products over reactants, and yeah, using the stoichiometric coefficients, which we already went over. And it gives us a little example of N2O4 degrading into nitrogen gas and oxygen gas. So we can see that we have the Kc being equal to the concentration of N2 raised to the first, being multiplied by O2 raised to the second. And they got the second because of the coefficient in front of oxygen. And all that being divided by our N2O4 raised to the first. And then it simplifies to all of that without writing the 1. Yeah. So the next page goes into Kc for heterogeneous reactions. And heterogeneous reactions are reactions that include, are those containing condensed phase components, which means reactants and products that are either solid or liquid phase. And it goes on to say, however, only aqueous and gaseous constituents are written in our Kc expression and used to evaluate K. Basically boils down to do not use solids or liquids because those are too condensed for us, basically. Kind of think of it like you have a bowl of cereal, and basically we're only interested in what happens inside the milk portion. So we're not interested in the actual cereal. We're not interested in like the liquid or the solids. So for Kc, we're only using aqueous and gaseous concentrations. So give us an example. Oxygen plus hydrogen yields water. So we have O2 in a gaseous state plus 2H2, also in gas, yields H2O. This is in a liquid phase. So we'll do the same thing that we always do. We do products over reactants. But because we don't have any products that are in either the gaseous or the aqueous stage, we'll just use a 1. So 1 over concentration O2 multiplied by concentration of H2 raised to the second power. And that's how we would get that. Any questions on KC so far? No? All right. So it goes on to more practical applications of KC, or basically how we're going to use KC with actual numbers. So it tells us to evaluate KC, the reactant and product concentrations are inserted into the expression, raised to their respective coefficients. And it tells us again that KC is unitless. And it gives us an example where A plus 2B yields C plus 3D. So we can see they gave us a bunch of different concentrations for each of those compounds. And they just plug it in, raise everything to their coefficients, and they got the answer of 10.7. And it goes on to tell us another example where for acetic acid, where acetic acid plus water will give us the acetate ion as well as hydronium, or H3O plus. And so they've written out the KC expression, and you'll notice that water is not included, and that's because it's in the liquid state. And yeah, so let's see. Let's jump to 213, these practice exercises. And let's try a couple of them. So let's look at number 1. So what it wants us to find is give the KC expression and determine its value for the given reactions on page 213. And determine its value for the given reactions under the stated conditions. So let's see, that first equation is 2SO2 plus O2 yields 2SO3. And then it tells us at equilibrium, concentration SO2 equals 0.052. O2 is equal to 0.32. And then SO3 is equal to 0.89. These are all like that. Oops. Oh, it's the same thing. All right. So we need the KC expression. So KC is equal to products over reactants. So what's going to go on top? You guys could just put in the chat.
SO3.
Mm-hmm. So
1, 2.
SO3. Just like that?
No. 2.
What do you mean 2? Like raised to the 2?
Yeah.
Oh, mm-hmm. So it'd be SO3 raised to the second power. And what goes on bottom?
SO2 and O2 power SO2 power 2.
Mm-hmm. So just like that.
Yeah.
Yeah.
And then plug in the number.
Yeah, so we plug in the number and we end up with 0.052. 89 squared over, what is this? 0.052 squared multiplied by 0.32. It looks like somebody had put it out. Let me see. The less math I do, the better. So we got 213. Oh, wait. Or is it the page number? That looks like the page number. But yeah, so we plug in all the numbers, and then we end up with a final answer of, does anybody have the final answer of that math right there? Let me see. 0.89 squared. 915? I don't know. 7921 divided by, let's see, 0.052 squared times 0.32. Yeah. So 915. Mm-hmm. So that's equal to 915. Cool. And that's plugging in. So number 2, basically the same thing. I'm sure everyone here knows how to get the KC expression. You guys seem pretty good at that. The rest is just plugging in. So number 2, we basically know the process. And number 3, really the only thing to note is you'll notice that they gave us our concentrations of B and D once we reach equilibrium. How come we don't have A or C? How come they didn't give us the concentrations of those?
We don't include them.
Mm-hmm. Yes.
Because they are solid and liquid.
Yeah. Good job. So solids and liquids, we omit. All right. So let's jump to the next page, 214. So plotting the reaction progress in equilibrium. Yeah. Basically, plotting the reaction progress to equilibrium is probably a better way to say it. Because once we reach equilibrium, nothing's happening. The concentrations will not change. So it tells us our similarities to plotting for unidirectional kinetics reactions. What that basically is saying that it's similar, but for a unidirectional kinetic reaction, or something that only takes place in the forward direction, let me make that a little better. So we got something like this, something like this. And we'll say this is unidirectional, and this is one that reaches equilibrium. So an example of a unidirectional reaction would be like dropping in HCl into a container. So we know that HCl, when dropped into water, because it's a strong acid, it will dissociate completely. So HCl concentration will go all the way down, and these two will go up. But when we're talking about reactions at equilibrium, what's going to happen instead So going back to that calcium hydroxide example, so CaOH2. Because calcium hydroxide will not dissociate completely, what's going to happen is it's going to go down to whatever concentration it is at equilibrium, and the presence of the calcium ions and the hydroxides will also go up. So it's not that one runs out, but rather they reach equilibrium where calcium hydroxide will no longer dissociate. And so because it's not dissociating, the concentrations of those ions will not increase either. Yeah. And that's basically what this is saying. So we have a guided problem down there at the bottom. So it tells us if 2 moles of nitrile chloride gas, NO2Cl, is pumped into an empty 5-liter reactor vessel at a high constant temperature, the reaction comes to equilibrium according to the chemistry. And it gives us the chemistry there. After equilibrium is established, 1 mole of nitrile chloride gas is present. Sketch a reasonable curve for the molar concentrations of the 3 substances, showing the progress of the reaction to reach this equilibrium position. So yeah, give us a lot of information there. So the first thing we're going to do, convert to find the molarity of the substances we have. So it told us we have 2 moles of nitrile chloride in a 5-liter vessel. So 5-liter, 2 divided by 5 tells us is 0.4. So 0.4 molar nitrile chloride. And from here, we can create an ICE table. So I hope you guys are familiar with ICE tables. Is anyone not familiar with ICE tables and wants to go over ICE tables? No? All right then. Okay, cool. So we create an ICE table. Thank you, Alejandra. So we have initial, our change, and once we're at equilibrium. So we have NO2Cl, NO2, and Cl2. So something like that. Cl. So initially we have 0.4 molar of that. It tells us that it's an empty 5-liter reactor vessel, and doesn't give us any concentrations for the other 2 substances. So we could assume that there is 0. So 0. And now we have change. So it tells us that after equilibrium is established, 1 mole of nitrile chloride gas is present. So we have to convert that mole into molarity again. So it'd be, well, let's see. So yeah, so once we're at equilibrium, I wonder why we need an ICE table for this. But anyway, yeah, so it tells us 1 mole of nitrile chloride as gas is present. Sketch reasonable curves for the molar concentrations. Yeah, so for change, we're going to use minus 2x, because we know it's going to change by some. And because we have a 2 here, it's going to be changed twice as much as opposed to that CL, for example. So CL will be having an addition of just x, because there's only the coefficient is 1, and then NO2 would be plus 2x. And then, of course, it's important to keep in mind what's negative, what's positive. We're gaining reactant products rather, so we have a positive for that and a negative for our reactants. So once we reach equilibrium, we have 0.4 minus 2x, and then here we have 2x and x. So our next step would be to calculate for x. So we know that our final amount of moles of nitrile chloride is 1 in 5, so it'd be 1 over 5. And 1 over 5 is 0.2. So we could say 0.4 minus 2x equals 0.2. And then we could go ahead, solve for x, subtract 0.4 from both sides, and then divide by -2. So we end up with x being equal to 0.1. And yeah, so, and we of course have molar. So after that, we just plug in equilibrium for NO2 would be 2x. So this would be equal to 0.2 molar. And then for our chloride, it's just x. So this is equal to 0.1 molar. So yeah, after we have all this information, I'm going to clear the screen. Once we have all that information, now we could plot out the progress of the reaction. So we start off with our NO2Cl. Then at the bottom here we have, what was it, Cl2 and NO2. So we know that once it reaches equilibrium, our nitrile chloride comes to a concentration of, what was it, 0.1? No, 0.2. So we could have 0.2 here, 0.2, and here we have 0.4. So it's going to go something like this. And we can say like right here is when it reaches equilibrium. So that's when the concentration doesn't change anymore. And then we could do the same for our NO2. So we start off at 0 until we reach a concentration of 0.2, where it'll flatten off. And then lastly, we have our chloride, our gaseous chloride, which will have a concentration of 0.1 at equilibrium. So it'll reach half as much. And yeah, so that would be reaching equilibrium right there. And then on page 215, it has a better looking graph. But yeah. And then the last thing it wants us to do, or last thing it shows us is calculating for the equilibrium constant. So we know the equilibrium constant, Kc, is equal to products over reactants. So we could just plug in for our known values. So our products, we had 0.2 and 0.1. And on the bottom, we have our reactant, 0.2. And then we know that our NO2 has a 2 before it. Same with our nitrile chloride. So it looks something like this. And then we go ahead and solve through for our final answer of 0.1 for our constant at equilibrium. Are there any questions on plotting? We've done a lot of plotting in the past, so hopefully not too confusing. Yeah, so we're going to jump to the next page, 216, where it tells us a little bit more about Kp. Kp, basically the same thing as Kc, but then this time we're only talking about pressure. So if we're only talking about pressure, one might be thinking that, we don't use solids or liquids for pressure. And another thing that we omit in this case would be aqueous compounds. So pressure, kind of think like gas, and we're using only gas for Kp. And it tells us a little bit more useful information in that little chart there. So Kp, similar to Kc, is unitless. However, Kp uses gases only. And it's important to know that it deals with partial pressures in atmospheres, rather. So yeah, we're gonna be working with atmospheres. So it tells us from the expression, values can be extracted to better understand the position of equilibrium for the reaction. And that kind of gives us a little hint at Q, so Q versus K. The Kp expression for the following generic formula is expressed below. A plus B plus C yields D and E, but it looks like they forgot about E and they misplaced C. So whenever you see like PC, BD, PD over PA, PB, consider the following reaction. So A plus, oh, that's backwards. B yields CC plus DD. So forget about that E thing. And then since we're dealing with Kp, everything has to be in gas. So yeah. Yeah. And then, yeah, it looks like there's a ton wrong with that section. But yeah. So it goes on to give us another example. A plus 2B yields C plus 3D. And it goes on to give us some values for all of these molecules. So they just wrote out the Kp expression, D raised to the third, B raised to the second, plug everything in, and yeah, they just solved through. They got an answer of 10.7. So same thing as Kc. The only thing important to note is that we have to use atmospheres. So let's look at the next page, 217. Let's give these practice exercises a shot. So it wants us to give the Kp expression and the value for the given reaction. Excuse me. So it gives us the reaction N2O4 yields 2NO2, and it gives us some values for our pressures. Something that I want to clarify that I'll bring up to the people in charge of this, but whenever we are writing pressures of a compound, we don't want to use the brackets because the brackets indicate concentration. So in this case, it'd be better to write N2O4 is equal to 18.6 torr. Yeah, just to let you guys know. So let's see. Who's here? Alexis. What is going to be our Kp expression? You can say it out loud, or you could try writing it out if you want. Or if anybody wants to shout it out, try writing it out. It's up to you guys. What is our Kp expression for number 1, page 217?
It's NO2, Kp equals NO2, and then to the second power over N2O4.
Like this?
Yeah.
Yeah, this is exactly right. So we got products over reactants. NO2 had the coefficient of 2, so it's raised to the second power. So yeah, knowing this expression, what is going to be our value for Kp? What is our numerical value?
Do we have to convert the torr to ATM?
Yes, we do. And the conversion factor is 1 atmosphere is equal to 760 torr. Let's see. So we got 1.27 question mark or 1.48 10 to the negative third, negative 3. It looks like 1.4 10 to the negative 3 is a popular answer. So I'll go with you guys. So yeah. So what'd you guys get for the pressure of N2O4? What do you get for the pressure of N2O4 in atmospheres? So I'm guessing you guys got 0.02 atmospheres. So yeah, basically just remember to convert to atmospheres when we're dealing with KP problems. Oops. So yeah, number 2, basically the same thing, just a different formula. So we have some products. So 2.44, not quite. It would be 0.0244. And we get that by, where's my pen? We have 18. So we have 18.6 torr, and we know that for every 760 torr, we get 1 atmosphere. So that would be how we convert from torr to atmospheres. So close, which looks like your decimal points in the wrong spot. And number 2, basically the only new thing is they introduce millimeters of mercury, and it's just important to know that 760 millimeters of mercury is equal to 1 atmosphere. So that's a conversion for that. But yeah, main idea, convert to atmospheres. So yeah, any questions over KP? No? All right. So we can go ahead and jump to the next page, 218. Let's got a completely different answer. Oh, okay. Let's see. There's some confusion. All right. So I guess this is for number 1. So we have N2O4 equal to 18.6 torr, 0.099 for your pressure of N2O4. Oh, for KP in general. Let's see. All right. So we can convert torr 760 ATM torr, and we end up with 0.000. No, 0.0244. And let's do the same for our NO2. 4.58 torr times. Oh, you see? Okay. Well, let's see. Let's finish this off. 760. That's supposed to say 760. Torr 1 ATM. And this one I got to be 0.006. So we would do products over reactants. We had NO2 on top, so 0.006. And this one was squared. On the bottom, we had 0.0244. And yeah, 0.006 squared divided by 0.0244. Yeah. So we got 1.48 times 10 to negative 3. So yeah. Glad that's cleared up. So yeah. We're going to jump to the next page if there are no more questions. And the next page goes into the relationship between our Kp and Kc and how we could go back and forth. So it tells us from the ideal gas equation, it can be shown that pressure of a gas depends on temperature, but is also linearly proportional to the molar concentration. Thus, Kp and Kc are related. And it tells us a little bit of algebraic manipulation can allow one to convert from Kp to Kc using the following equation, where R is our gas constant, T is temperature in Kelvin, so that's important, temperature in Kelvin, and N is the change in total number of moles of gas involved in the balanced reaction. Oh, sorry. Yeah. And it goes on to say, if the number of moles has not changed from reactants to products, then Kp is equal to Kc. And that's because we do the final minus initial. And if they're the same, then it'd be like 2 minus 2 is 0. So RT to the power of 0 is just 1. So Kp equals Kc. So you kind of have that in the back of your mind. So let's look at a practice exercise. I think it's the best way to approach this. So practice exercise number 1 tells us find the Kc value for the reaction at 12 degrees Celsius when Kp is 0.082. And it gives us the following reaction. So we're going to find Kc, so we can plug everything else in. So Kp we already have. So let's write our equation up here. RT delta N. So we have Kp, 0.082. We're looking for Kc. R is given to us 0.0821. What is our temperature? Are we going to use 12 or what are we going to use?
Converts to the Kelvin.
So we have to convert to Kelvin, which is given to us from Delian at 285. So 285, 0.15 if you want to be more specific, and delta N. What is delta N for this problem? What is our change in moles? -4. Yep. Well, not quite. Remember Does anybody else have an answer?
-1?
Mm-hmm. Wait. Yeah, so it'd be -1. Um, and it's -1 because you notice that A is in a solid state. So we're not paying attention to our solid state molecules. So yeah, no worries. So delta N is going to be -1. So we could do some algebra, divide both sides by this portion, and we end up with 0.082 divided by 0. Wait, what? No, yeah. 0.821 to 85 -1 equal to Kc. So that we get a final answer of, let's see, 0.821 times 285 to the power of -1, 0.082 divided by answer. So I got a final answer of about 1.92. So yeah, did anybody get anything different? No. All right, cool. Any questions on this section, relationship between Kp and Kc? Determine the value of A in orbit. Oh, that's cool. So let's look at number 2 on page 218. So it tells us determine the value of lowercase a such that Kc is the same value as Kp. So we're gonna do module 10 today. We could get into it. Yeah, this is the last portion. We have one more page of module 8. Yeah, let's do module 10 today. Do you guys know the date of your exam? By chance, it starts on the 9th. Let's see. Today's the 30th. Yeah. So we can start, yeah. So let's start module 10 today. I have the beginning of the PowerPoint kind of started. That way we can go over module 10 on the 6th and then maybe have the latter half of the workshop kind of like a review. Does that work? How do you guys feel about that? Because I don't have the PowerPoint. Oh, it includes module 11. Okay, yeah, it looks like we're gonna be crunched then. All right. So let's finish up module 8. We'll do module 10 and then 10, 11 on the next time. All right, yeah. Okay. All right. Yeah, we'll start module 10 today. So yeah. Page 218, the practice exercise number 2, tells us determine the value of lowercase a in order for kc to be the same value as kp. And if you remember in that top paragraph, it tells us if the number of moles has not changed, that's when kp will be equal to kc. So we see that the number of moles on the right side is 3 because we're not including c because it's a solid. So in order for kp to be equal to kc, what is lowercase a going to have to be? So it's going to have to be 2 because we want 3 on both sides. And b doesn't really give us an option, so we determine it to be 1. So it would be 1 plus 2. So little a is going to have to be 2. And so yeah, that next page tells us equilibrium expressions in reverse reactions. And the main point is that Kc or Kp values for the forward reaction are inversely proportional to those of the reverse reaction. So give us an example. For a forward reaction, we have 2.010 to the fourth. So since it's inversely related, the reverse reaction is going to be 1 over 2.010 to the fourth, or 5 times 10 to the negative 5. And yeah, that's basically that. Cool. So let's get started on module 10. Module 10's tons of fun. So let's jump to page 242. So let me see. Let me jump to my PowerPoint. I have a little bit of it. Let's see, new share. All right, so here we go. So module 10 talks about acid-base equilibria. So equilibrium when talking about acid and base reactions. So on page 242, at the top of the page, it gives us some formulas that we need to know. And it's a bunch of different formulas. But if you kind of break them down into like pKa, pKb is kind of the same thing, just with a B. So kind of you just have to remember half of them and know that you have to replace like your H pluses with OHs when you're talking about bases, and your POH. And yeah. So properties of water. So water is basically composed of 2 ions. So H3O plus and OH minus. H3O plus and H plus are kind of synonymous with each other. We use those interchangeably. You may hear people refer to H pluses as protons, and protons, H3O plus and H plus, all mean the same thing. Whenever you see that in literature or like in problems. So whenever you have pure water, some water is going to dissociate into its ions. while simply existing. So you have like a little container of water, pure water, and the concentrations of your protons and your hydroxide ions is going to be 1 times 10 to the negative 7. And we could find our Kw to be equal to 10 to the 1 times 10 to the negative 14. So that's important to know. So yeah, and then basically this little animation tells you what happens in water. Yeah, that's pretty cool. But yeah, so the next thing I was going to talk about is determining pH. So whenever you see like P and then something, think negative log of whatever is in front of the P. So when we're talking about pH, we're looking for the negative log of our protons or of our hydrogen ions. Whenever you see POH, we're talking about the negative log of our hydroxide ions. So yeah, when determining pH, wait, what is this? Yeah, so some more equations that it tells us is that pH and POH is equal to negative 14. And we can, going back to these expressions here, I have a little video showing how you can go from, if you know your pH, then you could calculate your concentration of hydrogen ions. And you can see those two equations on the left-hand side. H plus is equal to 10 to the negative pH, or hydroxide ions is equal to 10 to the POH. So I have a little video. So what you're going to do is divide both sides by -1. So you get negative pH equal to log H plus. And you're going to raise everything to the base 10. So 10 to the pH is equal to H plus to cancel out the log, because the log will have a base of 10. So 10 to all that. That's how they got those equations. So yeah, those are important to know. So let's talk about pH. You can see here that the closer we get to 0, the more acidic something becomes. And so an example there, HCl, hydrochloric acid, pretty obvious. It's an acidic thing. Right there in the middle, we have water, has a pH of 7. And the more we go to the right, or the closer we go to 14, we have a more basic compound. And an example there, magnesium hydroxide. So yeah. The next thing that the chapter goes into is some strong acids and bases that you should know. Strong acids, I hope you guys are familiar with. We've been having to kind of know those for a while now. And it also tells us some strong bases. And an easy way to remember the strong bases is that letter B that you could form on your periodic table. So it starts at lithium, goes down to cesium, and then that little curvature between, I think, rubidium, strontium, barium, and cesium. Yeah. So that's a neat trick to know your strong bases. And so, yeah, something important to note is we know that strong acids dissociate completely in water, and the same can be said about our strong bases. So our strong bases will also dissociate completely in water. And yeah. So next thing it goes on to tell us is ice tables, aka your new best friend. Not really, but yeah. So ice tables show changes in concentration whenever something is added. So suppose you have 0.25 molar HCl. What's going to happen? So what do you think the change is going to be for HCl? What do you guys think? So it's going to be negative 0.25. And we know this because we have a strong acid, so it's going to dissociate completely. So we can answer that next question. How much will HCl dissociate? It'll dissociate completely. So this next one is filling out that chart. So H plus, we have an increase of 0.25. Cl minus, we have an increase in 0.25. So knowing this, what is our pH? Remember that pH is equal to negative log concentration H plus. So what is our pH in this example? 0.6. Let's see. Negative. Where's log? Oh well. So I think someone said 0.6. That sounds right. I think I did it earlier. But yeah. So 0.6 would be our pH. So that's pretty acidic, pretty close to 0.6. So knowing this, let me see, what's on the next slide? So if our pH is 0.6, what is our pOH going to be? pOH equals question mark. What is pOH? Mm-hmm. 13.4 equals 13.4. And we get this from the equation pH plus pOH equals 14. So if we know one of those two, in this case we know pH, we could solve for pOH. Yeah. So this next slide tells us, suppose we have 1.7 10 to the negative 2 molar of barium hydroxide in pure water. So what's going to happen? It tells us how much it will dissociate and what is the pH. So we know barium hydroxide, we see OH, we know it's going to become more basic. So we're going to have an increase of hydroxide ions. So yeah, let's look at our ice table. So the first we want to consider is barium hydroxide a strong base? Yes or no? So we go back, look at that chart. We see barium hydroxide is part of that B, so we do consider it a strong base. So to answer that question, how much will dissociate? All of it will dissociate. So for change, we have negative 0.017. And once we reach equilibrium, we're going to have a final concentration of 0. So we can fill in the rest. So our barium ions will increase by 0.017. Because it is a one-to-one relationship, it's a 1 here, 1, and then 2. I think we'll put a little arrow here. So once we reach equilibrium, we have a final concentration 0.017. So yeah. And then finally, our hydroxide concentration is going to go from 0 to whatever 0.017 times 2 is, plus 0.034. 0.034, so that once we reach equilibrium, we're going to have a final concentration 0.34. And yeah, so the last thing we're going to look for is what is the pH. So I'll give you guys a second to try and solve for that. I'll do the same here. Ow. So let's see. Never get the answer. You just shout it out. $12.5. 1,47. Let's see. 12.5 for pH. That was pOH. Oh, true. So the first thing we're going to do, go from, since we only have our hydroxide ion concentration to work with, we're going to find our pOH first. So what we're going to do, plug in pOH is equal to negative log of 0.034, which we got to be 147 about. And from there, I just rounded to 1.5. From there, we could do the equation pH is equal to 14 minus 1.5, which I got just from manipulating the previous equation we were discussing, which gives a final answer of 12.5 about. And yeah, that is that. And this is, of course, dealing with strong acids and bases. So we know that it's going to be a complete dissociation of these molecules. But yeah, the next thing we're going to go over is dissociation constants and measures of acidity and basicity. So I'm going to clear the screen, and that's all the slides I had prepared. So let's jump to the whiteboard. All right, cool. Okay. So let me, this is bothering me. Clear. Okay. I don't know if you guys saw, there was like a little dot. Okay. So Page 247 talks about dissociation constants and measures of acidity and basicity. And basically what that is saying is we know we have strong acids and strong bases, but we also have weak acids and weak bases. And how do we measure how acidic something is or how basic something is? That's where we talk about Ka or Kb. And these are the ionization constants. So how likely something is to dissociate into its ions. Ka referring to acid, and Kb when we're talking about bases. So yeah, it tells us like a hard number how acidic or basic something is. So let's look at the examples it gives us. So we have CH3COOH being added into water, and it'll dissociate into its respective ions. So we have the hydronium and the acetate ion. And we have Ka equals H3O plus times the acetate ion over acetic acid. And this is, standard K stuff that we've been dealing with for the past couple of weeks, products over reactants. And we could do the same for NH3. So we have Ka of NH3 is equal to concentration of NH4 plus multiplied by hydroxide concentration, all that divided by ammonia. And it tells us at the bottom there, the larger the Ka, the stronger the acid and degree of dissociation. Thus, the greater the hydrogen ion concentration. And it tells us similarly, the larger the Kb, the stronger the base, the larger degree of dissociation. Therefore, greater concentration of OH. And it tells us also that keep in mind that only weak acids and weak bases have Ka or Kb values. And we kind of think this through. We have all this jumble up top, but if we have something that dissociates completely, on the bottom, we're gonna have a 0. So we can't divide by 0. So we don't give strong acids or strong bases A, Ka or Kb. And going back to those examples, NH3 added into water kind of acts as a base. So instead of Ka right there, we put Kb is equal to NH4 plus OH minus NH3. So just to clarify, Kb when we're talking about bases. And we tell it's a base because it produces hydroxide ions. All right. So we can go and jump to the next page, page 248. And actually, we kind of skip that right there. It wants us to, we could do the first one. First one being number 5. So write the Ka or Kb expression for the following substances. So hydrofluoric acid, HF, dissociates into H plus and F minus. Are we going to use a Ka or Kb for this substance?
Ka.
Ka. Hydrofluoric acid kind of speaks for itself. And we have products. In this case, we have H, F minus plus, bracket, bracket. On the bottom, we have H, F. So this is our Ka for hydrofluoric acid. Same as usual, pretty standard case stuff. So I won't go too into detail with that. So we could jump to the next page, 249. And 249 talks about relationships between Ka and Kb. So Ka and Kb are related through the following equation. So we have Kw is equal to Ka multiplied by Kb. And you recall from the beginning, we have Kw is equal to 1.0 times 10 to the negative 14. And it tells us, be careful when applying this equation, as it only applies to conjugate acid-base pairs. So one must be the conjugate of the other. Are you guys familiar with conjugate base pairing? I think it was module 9. But yeah. So it gives an example. So Ka for acetic acid is 1.8 10 to the negative 5. And so this Kb for its conjugate base will be 5.6 10 to the negative 10 because, and it tells us how it's solved for that. So we're looking for Kb, we know Kw, we know Ka, so we could just plug in, manipulate, and solve through. So the next thing it tells us is pKa and pKb. So I don't know if you remember from my module 8 PowerPoint, no, but whenever we were talking about modules something, but whenever we see P, we think negative log. So pKa, one can infer, we're looking for the negative log of Ka. And yeah, that'd be right. So we have pKa equal to negative log of Ka, and pKb negative log Kb. So because we're looking at the negative log of a substance, we can determine that the smaller the pKa or the smaller the pKb, the stronger the acid and the stronger the base. So keep that in mind. Try not to get too confused, because the larger the Ka, the stronger the acid, but the larger the pKa, the weaker the acid. So just as there are pKa, pKb values, we could solve for pKw. So pKw, sorry, pKw is equal to 14. So we have some practice exercises that it wants us to do. So we have hypochlorous acid. So hypo negative ClO, what is it? 3 CHClO. Oops. There. HClO, hypochlorous acid. Ka is equal to 3.5 times 10 to the negative 8. So it tells us, write the chemistry and the mathematical equation defining this value. So we drop HClO into water. So H2O. And it's going to dissociate. It's going to lose its hydrogen because it's an acidic compound. So it's going to become H3O plus, and its conjugate base, which is ClO minus. So that would be the chemistry for this one. The next thing you wanted us to tell is write the chemistry defining Kb for the base. And we can say that Kb is equal to Kw over Ka. I'm not gonna write the numbers. I'm sure you guys get it. We can just plug it in. And the last thing it wants us to do is find the pKa value for the acid, find the Kb value, and the pKb value for the base. So we could plug in, but as we're crunched for time, basically you just plug in. I'm sure you guys got it. So yeah. Are there any questions over pKa, pKb, Ka, Kb so far? Oh, you go ahead. Yeah. Yeah, it's basically the same thing as we've been doing. Rate constants. In this case, it's the rates at which acids do their stuff and bases do their thing. So yeah. So let's jump to the next page, 251. So 251 tells us how to determine pH from either the Ka or the pKa. So it goes on to tell us in that top paragraph, unlike strong acids, which completely dissociate, weak acids only partially dissociate. So we can use Ka to determine how much something would dissociate by. And so we use ice tables and we use the value of X to represent how much something will dissociate. Since we don't know how much will dissociate until we apply a little bit of math. So we have an example. Find the pH of 0.2 molar aqueous hydrocyanic acid in a solution. So we have HCN dropped into water. Let me give myself some more space. Plus H2O. This will give us H3O plus and Cn minus. So we could do our little ice table. And we have initial concentrations of 0.2 molar here. Water we know is a liquid, so we don't talk about water. H3O plus, 0. This one's 0 as well. So we know HCN is a weak acid, so we're going to lose X amount of HCN. And using our coefficients, 1 HCN, 1 H3O plus, 1 Cn minus, we can see that we get an increase of plus X and plus X. So that when we reach equilibrium, we have 0.2 minus X, and then we have X and X. So that is our concentration at equilibrium. So what we could do now is plug in for our Ka. So Ka is given to be 4.9 times 10 to the negative 10. So that's equal to our Ka. And we know Ka is products over reactants. So our products, our concentrations of our products are X and X. So we do X and X. All this divided by our reactants. In this case, our concentration of reactants is 0.2 minus X. So from here, we can do one of two things. The first thing we could do is solve out the equation. And when we do that, you'll notice that right here, we have X being multiplied by X. So we're gonna end up with an X squared, which is no fun. Because then we're gonna have to use the quadratic equation to solve for X. And that's a whole ton of nonsense that we can avoid. So what we can do is use a shortcut. And you'll notice that Ka is basically 4.9, and the important part is right here, 10 to the negative 10. So it is a super, super, super weak acid. So we can cancel out this bottom X right here, because so little is going to dissociate that it's going to round up to 0.2. And what I mean by that is, let's say we lose 0.000001 molar of HCN. That's basically 0.2 still. So that is our little shortcut that we're going to use for this problem. So we end up with this being equal to X squared over 0.2. So now it's much simpler to solve for. So we do 0.49 10 to the negative 10. So 4.9 times 10 to the negative 10 multiplied by 0.2, and then to the power of 1 over 2, so that we get X equal to 1.0 times 10 to the negative 1, 2, 3, 4, 5. 10 to the negative 5. So yeah. I think that's pretty cool. I think that was my prediction for how much we were going to lose. So yeah. So that now, once we reach, now that we have X, we could solve for our H plus concentration and our Cn minus concentration. We do that just by plugging in. So the last thing it wants us to do is solve for our pH. So since we know this is equal to our concentration of our protons, we can determine that pH is equal to negative log of X. And we could plug in 1 times 10 to the negative 5 for X, and we get pH to be, let me see, negative log 5. So yeah. Any questions on something like this? I know it's like some pretty crazy math to be introduced. But yeah. No questions. And something I like to do when doing a problem like this is kind of like logically check to make sure your answer makes sense. So we have HCN. We know it's an acidic compound, so it's going to become more acidic. So our pH checks out. It is more acidic than, like it's close to the acidic than basic or neutral. And we know it's a weak acid, so it's not like, if you remember previously we did an example of HCl, and we got like 0 point something for our pH. In this case, we got 5, so it's slightly acidic, not too acidic. So this checks out in my head. So yeah. Do you guys have any questions? Yeah, so let's do another problem. Let's see. On the next page, page 252, it gives us another guided problem. So it's going to tell us calculate the pOH of 1.5 molar hydroiodic acid in a solution. Hydroiodic acid, HI. HI, I believe, is a strong acid. So let's not do that one. Let's do, so 252 at the bottom, practice exercises number 1. So find the pH of the following solutions and tell us a little bit more, but we already have our Ka. So we have 1.5 molar HF, and it tells us our Ka is equal to 7.1 times 10 to the negative 4. So let's see, calculate the pH. So the first thing we're going to want to do is write out the chemistry of what's going to happen. So we have HF plus water will dissociate into H3O plus and F minus. So we have our ice table. Water we don't care about. Initial concentrations 1.5, 0, and 0. So yeah, this is everything that we could determine based off of what's given to us. So our change in HF is going to be minus X, because we don't know yet, not until we do our calculations. H3O plus, because it's a 1-to-1, plus X, and F minus plus X. So that at equilibrium, we have 1.5 minus X, X, and X. So now we can write out our Ka. So we have Ka is equal to 7.1 times 10 to the negative 4, which is equal to products over reactants. In this case, our products are X and X over 1.5 minus X. So yeah, once we get here, I guess one thing I forgot to mention earlier about the shortcut. If it's anything times 10 to the negative, oh, that's ugly. So in order for us to be able to use our shortcut, that raised to the power of blah, blah, blah has to be pretty small. So I would say if it's -3 or lower, you're good for the shortcut. So you get a little check. But if it's higher than that, you cannot use the shortcut. -3 is honestly kind of pushing it. -4, we should be good. But yeah, so if you don't use the shortcut, you have to use the quadratic equation. So let me get rid of that. So we have 10 to the -4, so pretty small. So we can use the shortcut. So we'll go ahead and cancel this out. And we're left with this once we simplify. So x squared over 1.5. So all we have to do now, we have x squared is equal to square root, oh no, oops, not yet. Well, we could do that. X is equal to square root 1.5 multiplied 7.1 times 10 to the -4. And this we just got by, moving some things around. So once we're here, we could solve for x. So let's see. We have square root. Oh, didn't mean to do that. Square root 1.5 multiplied by 7.1 times 10 to the -4. So Pablo got 0.03. And I got 0.03 as well. So 0.03 is our value for x. So we're going to plug that into our E portion of equilibrium. So our final concentration of our H3O plus is 0.03. So let's see. To find the pH, we will just take the negative log of our concentration of H. So what is our pH in this case? We'll do negative log. This is equal to pH. So 1.5. So yeah, 1.5. So once we're done with the problem, we'll go ahead and do that, the check in our head. So we know it's going to become more acidic, so 1.5 makes sense. We know it's a weak base, so it's not going to be something crazy like 0 point something. And we're looking at the Ka, and we see it's 10 to -4. And we can kind of think to ourselves, we know that when we did that one problem, 10 to the -10, it was like 5. So this is compared to that one, much more acidic. So it makes sense that it's more acidic than 5. So yeah, everything checks out. Any questions? We'll do one more. So the pH will be the same for all these solutions. Not quite. I'm not too sure what you mean by that. As we change the concentration of the acid in solution, the pH will also change. So let's say we had, like 5 molar of HF, it'll be more acidic. We only have to get one, I mean. Yes. If I'm if I'm understanding you correctly. Yeah. You only have to solve for one pH. Oh no, you're good. So that being said, I think that's the end of class. I think 10:20 is when class ends. So I think right here is a good spot to end off with. If you want to try going ahead, we only have one little section. So if you don't mind staying a little bit longer, the last portion that it talks about is calculating pH from KB or PKB. And you'll notice that, let me see, I'm going to clear the screen. If you read through right there, you'll see that in that ICE table we do minus X plus X plus X. And essentially, it's the same process for Ka. But in this case, we're using Kb. So in that example right there, we have 1.7 10 to the negative 9 is equal to xx over 1.5 minus x. So since we have 10 to the negative 9, we could use the shortcut, get rid of this x, and we solve x squared, 1.5, 7, 10 to the negative 9, and we solve for x, and we'll get our concentration of OH. And then from there, we could use similar processes that we've done in the past to solve for pH. So when we're talking about KB or PKB stuff, is basically the same thing that we just did, just with that extra step from converting pH to POH. That was a much shorter module than I thought it was. So yeah. If there are no more questions, you guys are free to go. I guess some housekeeping things. I will be entering grades hopefully by the end of today. So if you have any homework you need to turn in, go ahead and do that. Until which module? I think up until module 9 is due today. So yeah, whatever you guys need. I put in some grades this morning, but yeah. So yeah. Which homework is due today? I think module 9. But whenever you get in. Yeah. So you guys have a good one. Be safe. Would we always use X to find the pH and pH, not the current connection concentration? they gave us. So we would use the concentration they gave us. So in this case, they gave us the concentration. Looking at page 253, they gave us the concentration of 1.5 of our pyridine. So we are using it in like this equation right here. So we're dividing by that concentration. But the change is going to be minus X. So we are going to use X, but we're also using that initial concentration, if that makes sense, if that answers your question. Yeah, because I know what you mean. So we have like our OH, and then down at the E, at equilibrium, the value is X. If we were looking for the concentration of, what is it, pyridine? I'll just write PY. Then we could do 1.5 minus X. And whatever that answer is, will be our concentration of pyridine. But when we're looking for pH, POH, usually it's just X. Mm-hmm. All right. Cool. I'm glad. Alrighty then.